Good day everyone, and welcome to ASIGA's dental webinar series. My name's Graham Turner. I'm the Global Sales Manager for ASIGA. And this is part of our series of webinars where we'll touch on all dental applications where our 3D printers are being used in the production process. Today we've got a very special guest, but before I make that introduction, throughout the webinar, if you have any questions for myself or our guest, please send them in through the Q&A section or the chat box, and we'll look to answer those at the end. We'll have a session at the end where we can go through and answer questions you may have. So without taking too much of our guest's time, I'd like to introduce Dr. Alex Yusupov, who's based out of Melbourne, Australia. So to all of our international guests, welcome. Alex is a leading orthodontist, and he specialises in digital applications and using digital technologies to get the best for his treatment for his patients. And he does some really amazing things with the digital process. So Alex, welcome.
Thank you, Graham. It's a pleasure to be here, and thanks for inviting me. Hi, everybody. Thank you for joining. And I'm extremely happy to be here today and talking about something that I'm very passionate about. 3D printing in our office is a relatively recent addition to our workflow. We've been using 3D technology for about 8 years, fully utilizing it probably in the last 5 years, and doing a lot of printing probably in the last 2 or 3 years, with just about 2 months ago going completely alginate and plaster free, largely thanks to ASIGA printers and how easy they make things for us to use. How 3D models are used in our office is going to be my introduction to just what we're doing with the 3D technology and 3D printing. So usually this comes at the end of the lecture, but because half of you will probably fall asleep by the end of the lecture, I thought I'll get you excited earlier on. So of course, retainers. We use a lot of thermoplastic retainers. Essex retainers are my go-to, and we also do bonded retainers. Now, it's all very easy to do that on the model that doesn't have brackets or wires, but being able to scan a model with braces, a couple of weeks before the D-band appointment allows us to print that model. And this is a ASIGA print, and you can see the elastomeric chains. You can see the brackets, and alginate just doesn't even compare, because as you're taking the impression out, it usually tears. So we can have the lingual retainer ready for the patient on the day of D-band. So in the morning, the braces come off, retainer goes in, we scan yet again, and 3 hours later, we've got Essex retainers ready to be fitted. Sure Smile aligners, I was kind of hoping to include some of that in today's presentation, but I'll probably do another webinar if I'm invited, just on how to print aligner models in the maximum way, standing up without having breakages. And we've developed a little workflow that I'll share with everybody later on at some later date. But this is becoming an increasing part of our practice. We're doing more and more in-house aligners. And the ability to produce just the number of aligners that you need at the time without committing yourself to the whole 33 or 40 aligners. And the fact that I don't have to restrict myself just to less than 10 aligner cases because of my printing capacity means we can do full treatment cases, and we do today using aligners. Pre-ortho restorative, being able to simulate the final tooth positions orthodontically, and then build up the teeth if spaces allows us to do that at the start, is just such a great exercise. And using combination of softwares, we can do that. We can go to the pre-treatment model with final tooth shape, and then give a suck down or a mouth guard to the restorative dentist and have those teeth built up on the day that we start treatment. This has been a huge advantage in our patients, where instead of guesstimating the space, we can just close the space and we know we've got the right tooth volume. The other thing is you don't have to do a lot of 3D digital work to get the teeth just right. Get them close enough and then just use your composite and polish it. So today, instead of trying to find mesh mixer software to get the teeth to look like teeth, I just get the basic structure and then just add a little bit of flowable and polish as we go. And this saves us a lot of time and still gets the same result. Planning implant spaces before orthodontic treatment is huge. You print the model with final tooth positions, you make a suck down, you send that suck down to the implantologist, and there's their implant guide. I mean, they just can't get it wrong. And so for me as an orthodontist who has to then work around those implants, I know they're going to be in the right place. Being able to cut the model to whatever you want and just print one tooth. Because we can move the teeth, I don't have to size bands anymore in the mouth. I can just separate the teeth on SureSmile software and then export them and just print 1 or 2 teeth at a time and then fit stainless steel crowns on hypermineralized teeth that already have orthodontic brackets on them. Once again, this is something that you could not do with alginate or plaster. Or you could, but it would be very difficult. IDB, especially lingual IDB, I do a lot of lingual work, and we used to pay thousands of dollars in setup costs and brackets, and today this has just dwindled down to a couple $100, and I can get this done under 24 hours, and if really at a push, I can do it under 2 hours if I want to. Designing appliances that are patient specific has been just incredible. I don't have to fit these things inside the mouth and spend half an hour trying to get the wire to fit. I can print the model, get some 3D printed stainless steel bands and have this inserted in the mouth and don't have to put the braces on until those canines have been retrieved. We're using a lot of TAD supported distalizers, TAD supported expanders, and the slide on the right is my modification of an expander and turn it into a mesializer at the same time. We can do so many things today that 3 or 4 years ago we couldn't do that. And this is all done in-house in our lab. We can design systems to intrude teeth on one side and correct scissor bites on the other. We can augment our anchorage with a single TAD and just move that 3 without skewing the arch form and open up the space on the left 5 at the same time. This ability to look at the model in the lab and just draw a picture and your lab technician works it out is just incredible. And the framework on the right side is all 3D printed. Distalizers in the upper is not a problem, but mesializers in the lower is a problem. And this is one of my own designs where we have some bone plates at the level of 3-4, and we just create a custom mesializer based on skeletal anchorage. And this is what it looks like in the mouth. Same patient, upper and lower. And we can move those 6s all the way forward without retracting incisors. And we don't have to put braces on until those spaces have closed. So that saves about 12 months of treatment in braces for the patient, and we have perfect control. And this is probably like the pinnacle of inventions. This is a patient that has a lot of impacted teeth and cladocranial dysostosis, and he's been without those 2 teeth for a while, and we needed to get some more expansion. He's class 3 as well, so we need some protraction. And at the same time, we want him to look good, so we've added some removable false teeth on the same framework that is held together by 4 TADs on the roof of the mouth. And his ability to cope and now smile without having a flipper while we're opening up spaces and working away is incredible. And once again, this just was not possible without 3D printing. It's just something we could not do as little as 3 or 4 years ago. The next phase for me is actually now doing some metal design and combining that with 3D printing. So we're doing some hybrid fabrications where we virtually place the screw, the expand the screw in the model and then design the metal work around it. And then when it comes back, we have a metal work that fits the screw perfectly. So all we need to do is just bring the screw in, put a couple of solder joints on each side and polish it up, and it's done. So once again, this is becoming just so easy. You know, it takes about 5 to 10 minutes to get this this framework done once we've got all the 3D printed parts. So I'm just waiting for Asiga to make a benchtop metal printer, and I'll be a very, very happy orthodontist. Our 3D workflow really starts from the scan, and unfortunately, you then have to prepare the model, you have to output the model, you have to set it up for printing, you have to print the model, then there is a bit of cleaning and curing involved, and then you have to fabricate the appliance. 3D technology, without being able to put something out into the real world, is really not useful. I mean, it's all very nice to see pictures, but if you can't do anything with them, if you can't print them, then to me, it really falls short. And it's only recently that we've been able to start printing stuff with consistency and reproducibility that I'm really excited about. And what I want to do today is, rather than me talking about hypotheticals, I actually want to take a scan and I want to show you how we prepare these models in-house, how we print them and what we do post-printing, and then also give you some maybe tips and tricks about how to set up 3D printing in your own office to make it really high volume, really reproducible and efficient, because until you do that, it is going to be a little bit haphazard. So we have 2 scanners in our office. We had a third one, but we got rid of it. We have a Trios and we have a Dentsply Sirona. Now, the Trios scanner comes with software that we have to pay annual fees for. And to output a scan as an STL, there is an annual license fee, which I'll show you. The Dentsply Sirona is a little bit more open program, but it doesn't have a lot of inbuilt software that allows you to manipulate the scans. So once again, once you get the scan, you can't just go ahead and print it. We have mainly Asiga printers. We got rid of all the others. And I have 2 Asiga small printers, the UV385s, and we've got 1 4K printer as well. And at any one time, you walk into my print room, at least 2 of them are working, and the third one's probably just getting loaded up. How do the printers work? Well, basically, they're all the same. They have a moving platform, which is driven by a very precision vertical driven motor. They have a vat that holds the resin, and they have some sort of a light element that cues the resin. So if we look at this, it basically looks like this. You've got the platform, resin tank with a Teflon membrane, glass surface, and a UV light source. When the model is being sent to the printer, basically the program that sends the model slices it into the thickness of each print, and those slices are then sent to the printer. And this is basically what the printer sees at every layer that it prints. It prints almost like a relief map of the print itself. And it gets to the end. So the print process itself is very straightforward. With every layer, the motor drops the platform, the light source goes on, a layer gets cured, and the process is repeated. And it keeps going until every layer is printed. Understanding that this process is printing from upside down also makes it easy to understand why some printers work a certain way and why the speed of printing is a little bit different. So if we look at the print time, and to me, print time is very important because the longer it takes to print a model, the longer you really can't do much with that model. But the print time can be related to the printer factors. For example, speed of the motor, vertical descent and ascent. The strength of UV light, how long does it take every layer to be cured, and the exposure method. And this is where Asiga has an advantage because it has variable descent and ascent rates that maximizes efficiency and makes things a little bit quicker and slows the motor down just enough just before the layer is formed to make sure that you don't get disturbance in the resin. So there's a lot of research gone into it. But the main thing, I think, is main difference between different printers is the way the layer is cured by the UV light. When you look at the light source of say, a cheaper printer like Formlabs, and this is one of my printers that I am sort of not using anymore. It's a great printer, but it has a drawback. And the drawback is that to draw that layer that I showed you, it uses a single beam of laser to run it out and draw. So it's basically trying to color in a shape using a very, very fine pencil. So of course, it's going to take quite a lot of time. It's going to take 57 minutes to print this model flat, and it's only 159 layers. Now, it's not surprising that if you're printing the same model next to it, so now you're printing two models, the print time is longer because now the laser has to draw another shape. And if you draw another shape, it gets longer again. And not only that, but the position of the models will also alter the print time. So for example, you put the models there, the print time is a little bit less. So obviously the laser is traveling from left to right. So here it has less travel to do. So 1 hour and 31 minutes to print 3 models from 57 minutes to print 1 model is a big difference. Now, Asiga printers expose the whole layer in one go because they're using a projector to draw the whole shape at once. And that has huge advantages because it can take the same model that I just showed you with foam laser that would have taken 57 minutes to print, and it can do it in 17 minutes and 22 seconds. Same 158 slices. Now, it will be the same time for 2 models or 10 models or 8 models because it's exposing the whole layer at the time. And that's brilliant because that makes it so fast. Now, all else being equal, say the exposures and the way the UV generated, the other thing that creates extra print time is the resolution. So for example, if we go from 0.1 millimeter resolution to 0.05, we're actually printing double the number of layers for the same volume of resin, which means that if we take this model at 0.1 millimeter resolution and change it into 0.05, then the print time almost doubles. And that's not surprising. The printer is doing double the number of approaches and double the number of layers. Now, oddly enough, the amount of resin used is still the same, and the cost per print is still $2.24 a model, which is very, very cheap. The model height is another way that we get more layers. The taller the model vertically, the more layers you're printing, which means longer print time. So that means that if we print a model flat, it will take 17 minutes, 22 seconds. But if we put it standing or add another, make it double the height, then it's going to take longer. The model orientation falls in the same category. So if we go from flat model to a vertical model, we are increasing the print time, but we can fit more models on the platform. So in one print, we can do 24 models instead of 10 models. So this is sometimes better off. And it only means one clean, only means one curing process. So once again, this is quite a good trade-off. But be careful, model orientation sometimes can make very, very precise componentry less precise. So if I'm doing a scan of a tad on the palette and I want that tad to be beautifully visible, then I can't print that model standing up because there are some gravitational effects and some viscosity effects on the curing time that may cause a little bit of distortion. But if I print it flat, those tads are just superbly imaged and printed. So preparing models for printing is the most common phone call I get from my colleagues and my friends. They say, I just got a Asiga printer. What do I do? You know, how do I prepare it? So I'm going to take you through a process, and I'm sorry there's going to be a few videos. And this is going to be a resource, not for you guys to do it yourself, but for your staff maybe to look at how we do it and maybe attune or fine-tune their processes. So when we look at the scan that comes out of the scanner, this is what it looks like. It's basically a non-physical shape because it's an open shell. And as an open shell, it can't hold water, which means it can't hold resin, which means it can't be printed. So we have to create a closed shell to be able to print this model. Now, there are 2 ways we prepare models in my office, and the most common way is using 3-shape ortho analyzer because we're already paying for its license, and it does make things Very, very straightforward. Now, 3Shape is not a cheap software. So we have 3Shape Ortho Analyzer. We also have 3Shape Appliance Designer add-on, and we have an STL output system. So the STL output costs me $1,400 a year to be able to output the scans as STL files. The dongle is $875. I don't know what that means. The Ortho Analyzer software is $2,350 a year, and the Appliance Designer is $5,250 a year. So altogether, over $10,000 a year we pay just on software alone to be able to use this. So it's hefty, but it provides us with ability to do things and save money on the lab fees, for example. So when we use 3Shape Ortho Analyzer to base the models, this is the process we'll go through.
So we'll start with Trios Ortho Analyzer. And I'm just going to create a fake patient called sample patient. So I do that by just coming up here and just creating a patient. So let's call it sample patient. We can fill in all the data for this patient, but I'm not going to worry about it for the sake of this exercise. And once we've created this patient, it will put the patient here, and now we can add a new model set for this patient. So as soon as we click on that, it asks us to label this set. We'll call it as initial set. And the next thing the software asks us is to actually import the STL files. So this is easy. We just go and select the maxillary model and select the mandibular model and load them into the software. Now, once these have been loaded, if we can't see the lower model, we just retoggle it, and there it is. We can see that these models are raw, they're not finished, they've got these jagged edges, and while they are registered to themselves, they're not really registered to the frontal view, for example. This is not the front view, this is a view that's from the top and it's skewed. So at this point, we are just going to save these models, save the session for this patient, and once we've done that, we're going to go back to this patient, find this patient, and we can see there's our patient, there's the set of models, and we can see that there's a big exclamation mark around these models because these models have not been prepared. They are just still as we see them straight out of the scanner. So we need to prepare these models, and we need to choose the right workflow to do that. And the right workflow is this one here called Prepare Model Set, or we can right-click on the models and choose Prepare Model Set here. This opens up a workflow window where we are told by the software what the next steps are on the left-hand side. So we are just going to follow those steps really, really quickly. So we're going to set the landmark for the 1.6. We'll set the landmark for the 1.121. I'm going to choose somewhere in the middle here. And we're going to set the landmark for the 2.6. So that sets our occlusal plane table. The next thing the software is asking us is to set the sagittal occlusal plane. So we're just going to run a line like this. And if we're not happy with that line position, we've got some control points here that we can move and rotate and quickly set up the palatal sagittal plane. The next step is to select what we're keeping on the model and what we're not keeping on the model. So this is just done with little splines like this, where we just go around the model and we choose which areas we're keeping and which part of the scan data the computer can ignore, the software can ignore and discard. Usually a good idea to just check that over and make sure that we are happy with our selection. Now we'll do the same for the lower arch. So basically just choose the line which delineates which scan data is going to be used in the model and which scan data is going to be ignored. just adjust this line here. And once again, reasonably happy with that. The next step is to choose the bases for our models, and there are different bases available. We'll just stick with these ones, and here we can just click and drag the bases up or down, and we can also have a look at this view and maybe make the base a little bit bigger or longer so that it encompasses the models. Let's have a look at the frontal view again, make sure we've got about equal amounts of top and bottom visible. And next. So what the computer will do now is clean up the model, remove all the bits of the scan data that we don't want, and put bases on these models. And here they are here. And we can see that the computer's done a decent job of doing that. So we're happy with that. The next step it asks us to do, if we want to do any fine tuning, like any modeling, we can do that. We can smooth things over. I'm just going to skip that. Same for the lower. And now it shows us the finished product, the finished models. And if there were any blemishes that you wanted to remove, you could have done them in the previous step. And before I close this and say that I'm done, I now want to export these models so I can send them to the printer with bases and filled as they are. So we just click on this button here. It asks us where do you want to save these models, and you can see now they've been relabeled as original and based. So we'll save that, and it's changed automatically the location for the lower model, and we just click save and done. So now if we look at this patient, we can see that this patient has 7 models. There's no exclamation marks on these models. The reason there was a question mark on the sample patient is because other than the name, there's nothing else added to this patient. But these models are now ready for printing or appliance fabrication if we want.
Okay, so that was nice and easy. Now, one of the softwares that you can use if you don't have 3Shape software is Autodesk Netfabb, and there are lots of other softwares like Mesh Mixer and Blender. I use Autodesk Netfabb because it allows me to do a lot more things down the track as well, and it's just a fantastic software to use. I went on the website and had a look at the cost of Autodesk Netfabb, and it's only like $6,515 a year. And I was really surprised because this is not what I pay for it. So I got one of my associates to call and see what would it cost for a non-commercial lab to have software. And they said, well, we'll give you a demo license key, and when the demo period runs out, you should still be able to use the software, which I thought was pretty good. And he's still using it. This was over a month ago. My cost is actually about $357 a year. And this is what I pay as an annual license. And I get one license and I can use it on 2 computers at any one time, which is more than enough. So I think it's a matter of calling Autodesk Netfabb and finding out if you're a not commercial lab, what would it cost? And I'm pretty sure it's not over $6,000. I think that cost applies to engineering companies that use Netfabb for their flow assessment and material strength assessment. Now, interestingly, Netfabb is often used behind the scenes by most printers in their software to actually generate slices. It is probably the industry standard for generating slices for the printers to use. So this is how we create the same things that I just showed you with Trios without using Trios.
So now we're going to use Netfabb to trim models that come out of the scan. So we'll open up Netfabb. Once it opens, what we need to do is to import or add the models that we want to work with. So the way we do that is we just go File, Add Parts, and we're just going to go to the same sample patient, and we're going to add the mandibular original and maxillary original parts. Once these files have been added, so the first thing we need to do is we need to orient these models, and they're actually skewed a little bit to the left. So we're going to select both of these models by going to the left-hand window here and shift selecting top and bottom. And what we're going to do is we are going to look from the bottom of the model view, and we're going to use this gizmo to rotate both of these models to face the front. Once we've done that, we're going to just level the plane of the occlusion, and we just want to make sure that it is very similar from right and left. And just remember that both of these models have to be selected for them to move at the same time. Otherwise, if you just move the upper model, the lower will become deregistered or it will not be in the correct position. So now that that has been done, what we need to do next is quickly clean up these models. So I'm going to work on the upper model first. I'm going to switch the view of the maxillary model. And what we need to do here is we need to select the bits that we don't want. So the way to do that is we select the model and we're going to click on this repair part option, and we're going to use a brush to select the bits that we don't want. Now, when we first start using that brush, you can see it's quite large. So holding Control key on your keyboard and then using the scroll wheel, the wheel of the mouse, you can make that as small as you want. And what we want to do is we basically just want to draw a line that will allow us to create a space or break the shell into separate islands. And once we've selected that, we just hit Delete key on the keyboard. And we just keep doing that. Just once again, start drawing the line that we don't, of the data that we don't want. And we are just going to gently trim and remove the material that we don't need anymore. So this is a quick way of cleaning up those ragged edges, but once we're finished and we're happy with the bits that are sitting on the main island, we can just go apply repair. And here the program asks us, do we want to keep the old part or remove the old part? I'm happy to remove the old part. So now that we trimmed that model and we have separated the single shell into these little islands, we need to get rid of all this stuff. But if I select just one of these islands, the whole model gets selected because it is still seen as one shell. It is still seen as one whole shell with all these little islands in it. So what we need to do next is we need to separate this single shell into separate shells. So we right click on this model and we're going to this modify and we select split shells into parts. Do we want to remove the old part? Yes, we do. And once we've done that, we can see that every separate part has now been colored a different color. So now if we select one part of the model, it will just select that part. Now I can go and manually select all these little islands and spend a bit of time doing that. But there is an easier way of doing that. And the easier way is to actually just come up here to the left, and you'll find that instead of having a maxillary shell or maxillary regional part, we now have a group of parts. These are all the shells that have been split off the original model. So now we're going to find, well, which shell represents this part, and we can see that that's shell number 11. So we can safely select the other shells and just delete them. So everything but shell 11 can be deleted. And now our shell 11 can be renamed as our cleaned part. So it's maxillary, the original model cleaned. So that's the upper model done. We can just close that, turn it off and switch to the lower model. And now we'll repeat the same process for the lower model.
So here we are, we've cleaned up the upper and the lower models, and now we need to put bases on them. And once again, this is relatively straightforward once you know how to do it. So I'm just going to quickly show you how it's done.
So the next thing we need to do is we need to add bases to the models. So in this particular software, what we need to do is we need to extend the base and then cut it. So we're going to start with the top model, We're going to select the model. We're going to go back to the repair part menu. And now instead of using a shell or a brush to select the model, we're just going to select the whole selected model. There it is there. Now, what we need to do is we need to extrude this part, and we need to extrude it downwards so that the edges of the teeth move down and all of this stays up. And this basically allows us to add the base to the model. Well, it just so happens there is this option here called extrude surfaces. We're going to click on that. And now we have to choose in which axis do we want to extrude the part. And one of the reasons why I realigned the model in the 3D world was to allow me to use this Z axis just to move everything downwards or upwards. So by default, moving downwards means we're moving in the negative direction, and moving upwards means we're moving in the positive or in the upward direction, which means that this model needs to move downwards, always in the direction of the incisal edges. So it's the Z axis. We want to extrude it by 15 millimeters, and we click enter, and our model is extruded in the wrong direction. And the reason it went in the wrong direction is because I put in positive 15, whereas we need to add negative 15. So let's do that properly, and we can see that all our incisal edges have moved down and the base stayed there, and everything in between has been extruded. So let's apply that and say, okay, we're happy with that. It shows us what it's going to look like, and we're going to say, please apply repair and please remove the old part. So that's the bottom done. The top done. Let's turn that off for a second, and let's have a look at the bottom. So now we need to select the bottom. We're going to do the same thing to the bottom, but now we're going to move it in a positive direction. We're going to go to repair part, select the whole shell, extrude surfaces, select all, not just shell, sorry, extrude surfaces, and it automatically went to -15, but we want it to go to positive 15. And we're going to click apply to see what it looks like, and it looks pretty good. And now we're going to apply repair and remove the old part. So now we have extruded the lower model, but it is still an open shell. And we extruded the upper model, and there's still an open shell. And both of them have been moved in 3D world, 3D space by virtue of extrusion. So what we need to do now is we need to put these models back to where they were. We know that the lower model moved 15 millimeters up, and the upper model moved 15 millimeters down. We just need to move them in the opposite directions. So let's do that. Let's click on the upper model, and this time we're going to use the move option. And we know that we want to move this in the Z axis, and now we want it to move up, which means it's going to be a positive 15 millimeters for the up movement. And we're going to close that. And with a lower model, we're going to move it again, but now we want to move it -15 in the Z axis and close that. And now we've got the models once again back to where they were, but now we have all these elongated bases, but unfortunately they're still not flat and they're still not closed. So what we're going to do next is we're going to cut these bases, and in the process of cutting, we're going to close the cutting surface. So we're going to select the upper part. We're going to go modify, cut, pre-cut, and in this cutting menu, we're going to use the plane cut option, and we need to activate the plane just by clicking anywhere on the model. And here is our plane. We can see the plane is not quite positioned the way we want. This angle here needs to be changed to 0. So now when we look from the front, there's the plane. All these allow us to change the orientation of the cut. So if we turn it 90 degrees that way, it becomes a coronal cut. Let's go back to 0. If we turn it 90 degrees in the pitch, it becomes a sagittal cut. Let's go back to 0. But in the 0, 0, 0 rotation, it becomes a horizontal cut, which is what we want. So these allow us to move the plane up or down by the increment that we select. But here we can make it smaller or bigger. We can make this 2 millimeters or 3 millimeters, doesn't really matter. And we can move that plane up or down. And here is what I want to do is I want to cut this upper model, but I want to leave enough of the palette so that I can see the whole palette, just in case I want to fit a palatal appliance there. Now, if this was an Essex retainer, for example, we probably wouldn't need to have the model that high. So I'm just going to move this up and maybe leave myself a couple of millimeters above the roof of the mouth. Once I'm happy with the cutting surface, I need to select a few options here. So I don't want to cut anything other than the selected part. I want to use the plane as the cutting boundary. I want to stitch the parts together. I'm not sure what this does, but I just leave that on. I want to remove the original part. I don't want to have a nest of different parts, ones that have been cut, ones that haven't. And this is really important. I want to close the cutting area. I want this to make a solid shape. So when we click cut, the computer does its magic. We now have 2 parts in the upper model. They've been cut that way, and we select which one we want to remove. So we'll delete that part, and now you will see that not only has it cut it very cleanly, but it's also closed the shell and made it watertight. So we've done the upper, now we need to do the same to the bottom. So we're going to go to the same menu, we're going to go to modify, cut, pre-cut, plane cut, and you can see our plane is already visible, but it's up the top there. So we're just going to bring that down. To there, and I'll just check that I'm not cutting too much away on the lingual aspect of this model. Probably could go a little bit less. Doesn't need to be such a thick model. And yeah, I'm happy with that. Same close cutting area, remove original parts, stitch parts, use plane boundary, and unselected parts applies. And you'll perform a cut here. And now this model has been cut. So this is how we prepare models, but we have a problem. One of these parts is still not watertight. It's still showing us an exclamation mark that there may be a problem with this model. Well, what we need to do is we need to repair the part or prepare the part. So we do that by clicking on the lower model to start off with and going to prepare module, and we're just going to run a repair script. We're going to use default repair script, execute, and that gets rid of that problem. So now this model is watertight. And just to be sure and to be safe, I'll run the same repair script in the upper. Default repair, execute. This is good practice to always make sure that your parts are fault-free. Now that these parts have been prepared, we can go ahead and export them as STL, and it should go back to the same directory as original models were. If not, we select the model. And now we're going to rename this link and paste. Now, I always check this optimize box to make sure that there are no errors in the model, and I will do the same for the bottom. I'm just going to export the part, and we will check the optimize box here, and we'll keep checking that until we show 0 degenerated triangles. And we're going to go back to the same directory where the original models were. And now we're just going to relabel that as cleaned and paste. And now these models are ready for printing as well.
So now when we prepare these models initially, we usually leave the whole base in, but when we then go ahead and make appliances on them, we actually then go ahead and prepare them even further. We'll put labels on them so we know which patient they belong to. And also we may cut them even more, or cut them into sections. And once again, we use Netfabb for that. And I'm not going to show you how to do that, but this is basically the steps. We can do some very fancy cutting to get rid of the unnecessary material, and then put a label on the model top and bottom so that we know which model belongs to which patient. And now we're ready for printing. So we've gone from an open shell, top and bottom, to cut shells and labeled models. And now we're going to go to a Seeger Composer and start printing those models.
So now that we have our models ready, we now need to send them to print. So we're going to use a Seeger Composer, which is the program that comes with your Seeger printer. Now, every printer will have their own program. So for example, Formlabs has a preform. Some programs actually use Netfabb to prepare their prints. So we're going to create a new print job. So we'll click new, and we're going to choose which printer we're going to send that job to. I'm going to send it to a little Max UV2. And once I've set that, here I also need to set the material, and we can use all different types of material. There is third-party material that we can use, but I use dental model and the resolution at which to print. And we're going to print a 0.1 resolution. So now that we've selected that, our build platform appears. And for most people, when they first look at this, they sort of go, not sure what they're doing and what they're seeing. But what you basically want is you want your models to be oriented on the platform, to touch the platform, and then you can decide if you need supports or not. So the way we bring models into the printer platform is just by adding files. So we're just going to go add parts, and we're going to select the files that we want to print. We're back on our sample patient. And what we're going to do is we're going to select our label parts, just those two, and we're going to import them in. And here we have a number of options that allow us to select how these are going to be positioned. So we can auto place them, we can put them at the origin, which is basically at this corner here. We can put them just at the platform center, or we can put them as file. And depending on what I'm doing, I'll change this. And we can also set this as a default. So let's just place it as files and let's import them. Now, because we've placed them as files, it used the registration coordinates from the previous program. So that may be Netfabb or Trios. And you can see that these models are really not going to print because first of all, they're not sitting on the platform. And secondly, they're penetrating the platform. So what we need to do is we need to reorient these models. And this is something you'll need to do regardless of which printer you use. So first of all, we decided that we're going to print these models flat. So we're going to rotate these models so that this surface, the flat surface, sits against the platform. And to do that, what we need to do is select the model in question. So just click on it and then select this rotate facet downward and just choose which facet you want to face down. So that automatically rotates that model. And the next thing we do is we do the same to the other model and rotate the facet down. Now, the reason why I don't use angulation changes is because the model might not necessarily be at right angles or vertical when it comes in. So it's always safer just to nominate which surface you want to be flat. Now, I can spend a bit of time trying to get these models on the platform, but there is an easier tool called Autoplace. So by clicking on that, I want all the models to be placed on the model. I'm going to ask the computer to work out the best position for by X1 placement. I'm not going to create a base, but I do want Z leveling. And what that means is I want the models to be flat on the platform. So I'm just going to apply, and all of a sudden, these models have turned gold color. And that means they are now can be printed. Now, interestingly, if the models intersect, they'll still be gold. They'll just be printed together. So we just need to make sure that we don't have models intersecting. Then we just need to review that these models are sitting flat against the base. So we need to see this almost like a mirror finish of the model when you go from this angle to this angle. If not, if only part of the model is touching, the chances are the model is going to break off during the print process. If I was printing another model, let me just view and then just zoom to all. If I was going to print more than one model, then I would probably, or more than two models, I would probably rotate this model and try and get this into a slightly tighter configuration. So then I could probably print another model. The auto place, well, it's pretty good. It's not great. So you can always maneuver the models just by clicking and dragging. And your right click button actually allows you to rotate the model in one axis. But you can always nest the models a little bit tighter if you need to print more models than just these two. But we're going to leave it just like this. And we are now pretty much ready to send this to the printer. So you can see that the models are well oriented. You can see that sheen on the model, which means that it's going to print well. And now we just need to send it to the printer. And to do that, we're just going to print. So next, it tells me that two parts do not have support structures and may fail during the build process. Well, we're printing them flat, and I think that should be fine. It shows me the cross-sectional view. It asks me whether I'm using a fast print mode, and yes, I am. It does make a bit of difference. So it's 24 minutes, 44 seconds in the normal print, sorry, in the fast print module. But if I click that, it adds another 5 minutes to the print. Now, if I have a very, very delicate job and I want to make sure that it prints well, I might choose not to use the fast print, but I usually always have this on. There is no base plate, but if I had an uneven model, say it wasn't touching the floor properly or the platform, I could create a base plate and I could make it the shadow of the model. I could do a full base plate or a bounding box, which is basically when you click on the model, what you see is the bounding box. And the interesting thing is we can have it underneath the model or intersecting, and it's the intersecting one that we want if the model is not sitting flat on the base. And then we can nominate the thickness. And I think it only gives you up to about 2 millimeters thickness that it can add. Anything more than that, it'll say, no, I'm not going to give you more than 2 millimeters of thickness. So I don't want any because the models are sitting flat. So I'm just going to go next. It shows me all this stuff that I don't really need to know. But this is the bit that I want to check that the models are actually sitting flat on the platform. And now I'm going to send the build to the printer. So the computer is now slicing the model into 179.1 millimeter slices. And it will also ask me whether I want to preview the slices. And I definitely do, because I want to make sure that the first slice is sitting flat, that I don't have just part of the model touching the platform, because that's usually where it will fail. I don't normally go and sort of, look through every slice. There's no need for that, but this is basically how the printer is going to build that model. And lastly, I can actually, most printers now don't need you to go and physically turn the printer on and send it to print, provided that you are sure you've got enough resin in the tank and you are certain that the platform is clear. You can actually send the print from the computer that you're working on. So there's the front panel view, and I can just go to print, next build, which will happen to be today's print at 7:07. And build time 25 minutes. No, I don't want to shut down and finish, so keep the machine on, continue, make sure that it is the right material, make sure that the build area is clear, start build, yes please. And what will happen is the printer now will wait till the temperature reaches the allotted temperature. If it's within a couple of degrees, I just go skip and print, and then it will send the job to print.
All right, and so the printer's done its job. So it started, 27 degrees. I pressed skip and it started the job, and then it built the job. And what I love about a Seeger printer is it actually tells you how much use your tray has had. So if your tray has reached more than 100% of its use, it will not allow you to print anymore, which means you always have high quality prints, because if you don't have that measurable or visible, you keep using the same tray, even though the optical quality of that tray has degraded and your print quality has degraded. So how do we post-process these prints? Well, very simply.
So now the print is finished. We just come to the printer. We'll just gently open it up. We undo the screw here that holds the platform. slide the platform out, and then we just bring this over to our tray. And you can see that the models are printed, but a little bit closer. You can also see that there's a lot of resin still around. So we're just going to use this little scraper just to remove the models. Just give it a little bit of a kick like that. Now, as long as the models have printed well, I don't bother cleaning the base. It's just wasting a lot of resin. I'm going to put that back in. Now, make sure that there's still enough resin in the printer. And we will just leave this for the next print job. And you'll just press OK that we have taken the printer out. Then ultrasonic cleaning, we use isopropyl alcohol. So I've got 2 ultrasonic cleaners, dirty 5 minutes, and then clean 5 minutes. And so the beauty about having 2 ultrasonics here, we're going to take the basket out of the dirty one and put it into the clean. So having identical machines means that you're only using one basket at a time, and it makes it very easy. Once the models come out of the ultrasonic, they're pretty clean, they're pretty squeaky, there is no oil residue on them. You can air dry them, but we have a triplex in the area, so we just quickly blow dry them very quickly, and then we're ready to put them into our UV curing box. Mine has got double B on it because it's a BD box. No, it's not, it's a mistake. That cures it for 10 minutes, and the model is ready to go. So the models are now ready. They've been labeled, they've been printed. The print quality and the resolution is just superb. They are so crisp. I just love these models. Setting up 3D print room, we have just gone through a renovation because 8 years ago when we built our new practice, I did not imagine that we're going to be using 3D technologies. So this is our 3D print lab, and you can see that on the left side, you've got all the printers lined up in one row, and on the other side is my lab technician's workbench, and that's where all the metal work is done. All our suck downs are done in the plaster lab room, which is in the other corner of the office. Some of the highlights about the 3D print lab is that, first of all, you need to have easily accessible and sturdy bench space. You need to have benches that are not going to vibrate when somebody walks past, because if it's vibrating and the machine is printing, it may cause a misprint, although I don't believe that's a big issue. You don't want external direct sunlight because it will cure the resin if it hits the printer long enough. So this is the room doesn't have any external light. You don't want a lot of dust. You do want a sink because you want to be able to rinse and tip things out. Shelves for resin trays, a lot of storage required. Plenty of power points, compressed air, and we've also placed an exhaust fan because IPA, when it first comes out, is quite strong, and it's nice to be able to evacuate that air really quickly. So that slide on the right side shows the vent for the air, and there's the air next to the air conditioning vent. We've got 2 of those vents happening, and you can't even hear it. It's roof mounted. We've got roof above us, so it's not a problem. Consumables. Resin tank costs you about $200 to $300, depending whether it's a 1 liter capacity for the small machine or a 2 liter capacity for the big printer. The resin itself, model resin, there are different types. I like the one that a Sega makes, and that is somewhere between $160 and $250 a liter. But some of the specialized resins can cost you up to $1,000 for half a liter. Like inlay material or composite restorative material, which I've just used recently. It's beautiful material, but the 500 ml bottle cost me about $1,000. But that 500 ml bottle can probably do hundreds of little inlays and onlays. So it will provide a lot of use. Consumables, isopropyl alcohol. During the COVID lockdown, there was no IPA in Australia because everybody was using it for cleaning, and the prices skyrocketed. But I couldn't get any. It was really hard. So now we always keep 20 liter drums, a couple of them extra. And before COVID, they used to be $125. Now it's $176. The gloves and paper towels are really important. And also, if you like your nice RM Williams boots,
and nice shoes. Try not to wear them in the lab, because if you spill a bit of resin on that boot is damaged. And I've lost a couple of RM boots, but I've just discovered that RM Williams will actually repolish and repaint them for $55. So 3 of my pairs are being redone. The crates that the Sega 4K comes in, it's a piece of art. I was so sorry to throw it out, but I had nowhere to put it. But if I had little kids, I'd make a cubby house out of it, or make some sort of a storage or underbench space, or even a workbench. It is just beautiful. Equipment, ultrasonic baths. You can use water in your ultrasonic and then have IPA in little jars or beakers. Some people use peanut butter containers. I find at some point there'll always be a bit of water getting into the IPA and IPA getting into the water. So I've stayed away from that. What I do now is, if I have a small part like a restorative material, it's got to be certain color, then I will put it on its own into a beaker of IPA, so it's not contaminated by other colors of other resins. But what we discovered is, out of all the ultrasonic size, and I've got the 3 liter and the 25 liter ultrasonic, I find 6 liter works the best, because you're using about 2 liters of ultrasonic IPA in each one, and we rotate. So we go from clean to dirty, and then clean becomes dirty and dirty becomes clean. The curing lights, flash cure from a Sega, I think comes with a printer. I could be wrong, but I like this LC 3D print box, because it can take 20 models in one go. But both work very, very well. And if mine is tight, just use the flash cure. I've got them sitting as a backup. Ultrasonic baths, clean unit becomes dirty unit. A dirty unit, change IPA to make it clean. So it means that each bath gets used twice. Which means we're saving the IPA and still getting reasonably clean models. So it's been my pleasure to take you through our 3D workflow. I hope you found it informative. I think I'm 4 minutes over time. This was an hour and a half lecture before this. And I'm really, really grateful for the opportunity to share some of the stuff that we're doing and some of the processes that we've put in. Thank you so much.
Thanks, Alex. That was great. For anyone who'd like to get in contact with Alex to ask any questions, I'm sure, well, there's his email address, so I'm sure I'd be happy for you to get in touch with him. I've got a couple of questions here. I'm just question about the setup. Like, when do you actually use? When do you decide to use 3Shape, and when do you decide to use Netfabb? What's the thought process there? How do you?
All right, the 3Shape is used pretty much for every model, because it's done by one of my staff. She's the same girl that prepares all my photographs and prepares. So basically, she will base the models, but my laboratory girl will only use Netfabb, because then she will cut that model further into what she wants. And we also use Netfabb to do some minor repositioning. It's just easier than using 3Shape software to section the teeth. So I basically pretend that I'm using a little plaster saw to cut the teeth and move them, and my lab girl does it by herself. I use Netfabb a lot for fabricating other things. So, for example, to add a virtual screw to the model, I have to take it out of the 3Shape environment, because it won't let me do that. So I do a Netfabb, and then I reintroduce the model with the virtual screw or cradle or TAD back into 3Shape appliance designer, and a design appliance around it. There are a lot of workflows that you create, and you're basically just hammering little bits together to make it work. But it is becoming less and less of a problem than it was 8 years ago, when we first started using 3D software in a big way. There were a lot of disconnected parts, and the move is now to make things more and more connected. I like hollowing models in Netfabb. I like trimming them. I like labeling them. It's just easy. It's a software that I'm very, very familiar with. And I love doing my 3D wax ups in Netfabb, because I can use somebody else's tooth models and just put them on and move them in 3D space. without having to learn another software. So for me, Netfabb works very well. But if I didn't have Netfabb, I'd probably use Mesh Mixer. I just have to learn how to use that properly.
Yeah, okay, cool. The other one is, why have you chosen to have a large Pro 4K printer when you've got two of the desktop Max UV? Why have you selected that combination of printers?
You see, a Sega allows you to use different materials, and not all of the materials have to come from a Sega. So there are lots of companies like Whitmix and Keystone and Ceramco that make really nice restorative stuff. Now, that restorative material is, as I said, about $1,000 for a 500 ml bottle. Now, the big machine takes a 2-liter tank. So that means I have to put at least a liter in that tank for it to be able to print something. And then I would use it and then won't use it for months, and I'll put that tray away and all that material will just sit there. So having a small resin tank and a small printer, I can do very, very small things, and I can have only a small amount of material in the tank, and then I can put the tank aside in the drawer somewhere in a dark place, and when I need it again, I can use it again. The other thing is, Graham, I think I'm right, but I think the little machine is actually a little bit more capable. It can print, or is the big machine does the same? Because some materials are actually designed for the smaller machine.
So how do you mean from the compatibility with materials?
For the like restorative stuff and stuff, are they both equipotential or some materials they are? So I was wrong about that. So I think it's basically just saving the volume of material and being able to use multiple materials without having to buy liters of the stuff to fill a big tank.
Yeah, I think that's fairly common. We've got a few users around the world that will have, they may have started with the Max UV and they've looked to get something bigger. And it's a good complementary system for that very reason.
And having two little machines and then a big one also means that we may have a D-band at 9 o'clock. So we can get those D-band models for Essex retainers starting to print at 9:20. And then another D-band at 10 o'clock, or at 9:30, so that while the first one is still printing, we can get the second patient's models on and start printing those. And then at the same time, I might have a liner insert and I need to print 10 aligners for this patient. So the big machine is doing that. So it means you have these variable times of starting and stopping jobs without waiting for the same machine. And there's also redundancy. If one machine for some reason needs a recalibration, although hardly ever happens, you can get the job going on the other machine. So it's really nice. I wish I had another 2 little ones or something like that, but we can't justify the volume yet.
Yeah, you'll get there.
And lastly, we had to get another little one because Graham took 6 months to get the 4K to us. I think, did we get the second machine in Australia, or we waited for a little while for that, but we finally got it.
Yeah, I'd have to get back to you on that. I'll confirm.
It was nice.
Yeah. All right. Well, that's about it. Alex, there's no other. Let me just check this other screen and see if there's any other coming. No, that's it. So I'll just finish off by just letting everybody know that they can follow us on a number of different social media platforms. So we're on all the platforms there, so you can keep up to date with the SIGA news. And finally, Alex, thank you very much for your time tonight. It's Friday night here in Australia. So we're broadcasting from the future. So we're going to go and relax and have a nice weekend. And I wish the same to everybody else who's joined tonight. So thanks again, Alex. I really
thank you so much for joining, and thanks for spending the time with us. All the best.
Okay, thanks everyone. Take care.